Dr. Pavier is the group leader of the Radiological Materials Group at the Pacific Northwest National Laboratory. She's also the chair of the Gen 4 International Forum Education and Training Work Group. Patricia.
Yeah, good morning. Thank you so much, Bertha, and good morning, everybody. I hope you are doing well during this COVID-19 crisis. Like Bertha said, we're very happy to have Sam Supia with us today. He is currently the manager of the Chemical Engineering Branch and the Facility Authority for Trillium Facility Operations at the Canadian Nuclear Laboratories in Chalk River, Ontario. He received his chemical engineering degree and his PhD from the University of Birmingham in the UK and worked for a contracting company and British Gas Corporation in the UK before joining CNL. He's a professional engineer in Ontario and a certified project management professional. He has more than 35 years of expertise in different areas where he has been leading collaborations with industry, institutes, and universities. His current focus at CNL in the area of hydrogen production is in the development of the hybrid copper-chlorine cycle. This development is approaching lab-scale continuous operation demonstration in 2021. He is the Canadian delegate for and the current chair of the Gen 4 Very High Temperature Reactor Hydrogen Production Project Management Board. He is also a board member of the Canadian Hydrogen and Fuel Cell Association. He has been a regular presenter at IAEA's technical meetings and other national and international meetings on hydrogen production. Again, thank you so much, Sam, for delivering this webinar today, and without any delay, I give you the floor. Thank you, Sam.
Thank you, Patricia. Dear colleagues, good morning, good afternoon, or good evening to all of you, depending on where you are in the world. I hope everyone is healthy and hopeful rather, under the current environment, and helpful too. My presentation is on the activities of the Generation 4 Forums, Very High Temperature Reactor Hydrogen Production Project Management Board. Really a mouthful. In short, it is really hydrogen PMB. I would refer it to it as hydrogen PMB. My presentation will give a quick outline of the hydrogen PMB board itself, the current hydrogen production technologies and advanced technologies that our member countries are working on, and their current progress. This slide shows the GIF governance structure, basically, and how the project management board here fits into the structure through a steering committee to the policy group. Essentially, the PMB is established by the signatories of each project arrangement in order to plan and oversee project activities. Their main goal basically is to establish the viability and performance of the relevant Generation 4 system in their technical area. The flags in this slide shows the current members of the board. France, US, Canada, EU, Japan, South Korea, and China are the current members. The individuals who officially, these are the individuals who officially are part of the board, the current board, the hydrogen PMB board. This slide shows the chairs and co-chairs of the board since the project arrangement was approved in 2008 for the first 10-year period. The project arrangement is now extended for another 10 years until 2028. Normally, the chairmanship of the board is for 2 years, and the member countries take turn on a rotation basis. At the beginning, we needed three or so to face-to-face meetings a year to establish and implement the project plan. But with time, we have learned to be more efficient and have come down to a maximum of 2 meetings per year, sometimes only 1. We also rotate the country that hosts the meeting. The graph shows here how many times the meetings were hosted by the different countries. The last meeting was held in Shanghai in November last year, just before all the COVID issues came up. Currently, Canada, these were the chairs over the years. Currently, Canada is chairing the board, that is me, and Korea is holding the vice chair position. China, as you can see, China is still an observer, not a full member, but with the current finalization of the project plan, the accession is imminent. The VHTR project hydrogen PMB activities. The VHTR, I have to move this. The VHTR hydrogen production program basically aims at developing and optimizing high temperature thermochemical and electrolysis water splitting processes, as well as defining and validating technologies for coupling any Gen 4 hydrogen nuclear reactor system to such hydrogen production plans processes. So this slide shows the evolution of the different reactor systems over the last several decades, from generation 1 to the generation 4. The current generation 4 reactor systems included in the GIF are shown on the slide. Although the hydrogen PMB is under the VHTR system, hydrogen production processes that are better suited for the other reactor systems here, that are shown here, are also included in this PMB to make it more inclusive for the benefit of GIF. I'm sure all of you are aware that hydrogen basically is a critical energy carrier for now and future because of its high specific energy seen in this the top graph here. As the graph shows, for a unit weight, it really packs in the highest amount of energy compared to all other fossil fuels. That is, it has the highest gravimetric energy density of any known fuel, about 3 times. This is about 3 times that of the gasoline that you see here. However, because it is a light gas at ambient conditions, its energy density per unit volume can only be decent if it is sort of contained at a high pressure, as shown here. For example, here the hydrogen is something like 100 megapascal pressure conditions. For automobiles, for example, it needs to be compressed to something like 700 bar, that is about 70 megapascal, to cover a distance similar to a gasoline-fueled car with full tank of fuel. The demand for hydrogen, as you can see over the years, has been growing with the expanding population of the world. Because it is a raw material used to produce fertilizers and various other materials, its demand is growing and is only expected to grow even faster. With increasing living standards, for example, of the developing world, the demand for hydrogen is forecast to grow, as I said, very rapidly. In the future, to minimize the greenhouse gas emissions from heavy-duty vehicles, it's very likely a shift will have to be made to hydrogen fuel. This slide shows the some of the current available hydrogen production processes. Currently, something like 80 to 90% of the hydrogen is produced from fossil fuels here, through what's called the SMR, steam methane reforming process, and partial oxidation process, and a few other processes. These pictures show the various the two main processes. Something like every ton, for example, ton of hydrogen produced this way would throw something like 10 tons of CO2 into the atmosphere. Yes, there are methods available, conventional electrolysis of water, conventional cleaner methods available. The conventional electrolysis of water, alkaline or PEM type, using electricity as a using basically electricity. However, the electricity has to come from a clean source of production. The other issue is that electricity is not cheap, and the current electricity producing technologies are not as efficient as they should be or could be. Generation 4 reactor systems can produce electricity more efficiently, and therefore should be beneficial even for these low temperature electrolysis for hydrogen production. However, when you convert the heat produced by fission, by a nuclear reactor, by any reactor systems, to electricity, in the current systems or future systems, you lose a significant amount of the energy as waste heat, and hence reduce the efficiency. The heat to electricity conversion efficiency of the current commercial reactor systems is about say something like 33%, and the advanced reactor systems can be something like in the mid-40 region. Still significant waste of energy on the conversion of heat to electricity. What if there is a way of using the heat directly, heat produced by these sources directly to produce hydrogen, so that you do not have to lose the efficiency in the conversion of heat to electricity? Yes, there are hydrogen production processes that can utilize mostly heat to deliver hydrogen. However, as we'll see soon, these hydrogen production processes require high temperature heat. I would say this is one of the main reasons why many clever people in the past decided that producing hydrogen using advanced nuclear energy systems that can deliver heat at high temperatures is a good idea for large-scale hydrogen production. So why are high-temperature processes better for hydrogen production? Using the first and second law of thermodynamics, one can derive an efficiency term for the splitting of water shown here. As the efficiency equation shows here, the higher the temperature, the TH is the temperature at which the splitting process takes place, and TL is the temperature that the outlet temperature or the ambient conditions. As this equation shows that, if, for example, if TH is high, this term will be small, hence the efficiency will be large. So in a sense, with increasing temperature of the process, your efficiency would increase. So as part of an earlier energy research initiative called NERI, N-E-R-I, A study sponsored by the US Department DOE, a General Atomics team supported by Sandia National Lab, SNL, and the University of Kentucky sort of looked at about something like 115 different thermochemical cycles that produce hydrogen. Out of all these processes, the four processes shown in the slide have been receiving the most attention over the last decade or two. And these are the processes that the hydrogen PMB member countries are mainly focused on. The SI, the sulfur-iodine process was, and sometimes it's called iodine sulfur process, but I call it as sulfur SI process. It's a closed cycle based on three main steps. One exothermic step called the middle one, the Bunsen reaction producing sulfuric acid and HI at around 120 degrees C. Another endothermic step, decomposing the hydrogen iodide produced from the Bunsen reaction into hydrogen, the product that we want, and iodine to recycle for the Bunsen reaction. And the other endothermic step, the sulfuric acid decomposition into oxygen, the other product of the process, and SO2 for recycling to go back into the Bunsen reaction. And this step takes place around 850 degrees C. Hence the need for a high temperature source, heat source, to accomplish this step. A somewhat close relative of this sulfur-iodine process is the hybrid sulphur process, which utilizes the sulfuric acid decomposition step, similar to the sulfur-iodine process, but uses a what's called a SO2 depolarizing electrolyzer to basically to produce the hydrogen and the sulfuric acid to recycle. The copper-chlorine cycle, hybrid cycle, utilizes three main steps: the electrolysis, hydrolysis, and thermolysis, with an additional step of the separation process, separation step. Basically, an aqueous acid solution, CuCl acid solution, is electrolyzed to produce hydrogen and CuCl. More details will follow in the slides coming soon. There's one step, for example, this step here, what's called the thermolysis decomposition step, requires something like 530 degrees C. Hence, it is better suited for the whole cycle. That is the highest temperature requirement of this cycle, suited for moderate temperature nuclear systems, such as supercritical water or molten salt reactor systems, or solar energy. Since electrolysis is involved in these two processes, the CuCl and hybrid sulfur process, they are called hybrid sulfur processes. The fourth one is a high temperature electrolyzer of steam. This one here, a reverse of the solid oxide fuel cell technology. Generally, the electrolyzer functions very, very efficiently at around 800 degrees C, but also can function at temperatures as low as 700 degrees C. This slide basically captures the kind of work being done in the sulfur-iodine process under its own work package. So as part of the hydrogen PMB, each member state does its work in the various cycles and provide the input to the work package that is created as part of the hydrogen PMB in the various cycles. So this one, the Sulphur-Iodine process, has its own work package where the process engineering aspects, materials and their mechanical strength and corrosion resistance properties, the catalyst used for the decomposition of hydrogen iodide, sulfuric acid, their purification, bench scale testing, pilot scale testing, and the lifetime studies, etc. This kind of work are all reported as in this work package. These are all critical aspects of the process development, and they are covered in here. This slide shows the work done on the high temperature steam electrolysis, and again it involves process evaluation, development of advanced materials for electrodes, electrolytes, interconnections, stack designs, lab scale and pilot scale demonstrations are covered here. One interesting area, a growing area, is in the CO2 co-electrolysis. Basically, you feed CO2 with steam to into the electrolyzer to produce syngas, synthetic fuel. So what you get is carbon monoxide and hydrogen, which, as you would know, that can be used to produce various chemicals. And this is a growing area that many countries are interested in. This slide shows the development of the copper-chlorine cycle, the work package that covers the development of the copper-chlorine cycle, and other sort of cycles such as hybrid sulphur, and also any other cycles that might come on stream as time passes by. This work package covers the hydrogen production and nuclear reactor coupling. And it sort of looks at various aspects. This work package covers basically development methodologies and safety standards for individual processes and their coupling to nuclear reactor systems. Economic evaluations are also included in this work package. So to give some more details on the various hydrogen production processes. So this slide shows some details of the sulfur-iodine process. As I mentioned before, there are three main steps in the process within the overall process, and these are fairly sophisticated operations that these individual steps require. For example, in the HI process section, there are many operations. So the HIX solution that comes in here needs to be purified. Then it needs to be concentrated using a technology called EAD, electrodialysis method. And then it goes through a distillation system, and then decomposition reactor, separators, etc., before the hydrogen is separated and provided, and the other materials are recycled, sent back to the Bunsen reaction itself. Similarly, the sulfuric acid section has purification operations, concentration, the decomposition, which basically the sulfuric acid gets decomposed to SO3, and then SO3 gets decomposed to SO2 and oxygen is a product. In the Bunsen reaction, the reactor itself, there are various, it is a complex reactor systems. Then there are separators of the liquid phases, liquid and gas phases. It is truly a complex chemical process, but it has the potential to offer major benefit of high efficiency in the hydrogen production capabilities. Actually, many countries have been interested in developing this process. US and France collaborated on the development of an integrated, what was called an integrated laboratory scale experiment in sort of in the 2006-9 period. Much of their experience and the results have been captured by the hydrogen PMB in kind of as background IP reports. Further developments, unfortunately, further development of this process by US and France was abandoned to basically enable focusing their effort on the high temperature steam electrolysis process development in both countries. That sort of followed a down selecting exercise that was conducted towards the end of the first decade in 2000. However, Japan, Korea, and China have continued the development of this process very successfully, I should say. So this slide shows the Japan's progress under JAEA's support or work. Starting with their, in fact, with this lab scale testing in the 90s, they demonstrated that you can produce hydrogen using this process. In fact, they operated the reactor, this system, for 48 hours to produce hydrogen continuously at something like 1 liter per hydrogen rate. And that sort of demonstration, the successful demonstration, encouraged them to move on to the next phase, which was a bench scale testing, bench scale system, which was operated continuously for about a week. That's about 175 hours to produce hydrogen at about 30 liters per hour rate. And then they this demonstration was sort of followed by R&D activities over the next several years that focused on the various issues that they uncovered or discovered in the operation of these facilities, mainly materials related. The above focus, in fact, contributed to their next phase of their development, this system here, which is 100 liters per hour capacity, built with more engineered components. So this slide summarizes Japan's efforts since 2010. Focused on integrated tests of components, these various components, to both liquids and gases. There are both liquids and gases in the system. Exposures to components over 150 hours at a hydrogen production rate of 30 liters per hour here. And actually that work really showed that some of the materials that they had selected and used had a decent behavior under these conditions. Their current focus is underway to acquire more materials related data on long-term testing and basically the exposure of materials to these processed fluids and gases. So this slide shows basically the demand for hydrogen that Japanese expect over the next several decades, and how Japan is going to sort of satisfy such a demand, at least partially, using their high temperature gas cooled reactor technology that they're developing, integrating it with the hydrogen production process. This slide also shows the high temperature gas cooled reactor cogeneration capabilities, that is to produce heat as well as the the electrical power to produce the kind of hydrogen production rate that they've shown here. This slide basically sort of summarizes what I just mentioned. So China has been very actively involved in the sulfur-iodine process. This slide shows their progress from sort of fundamental studies in the early 2000s through system integration, fundamental studies, system integration, key component studies, and then the ambition to couple the hydrogen production process to their HTR-10 nuclear high temperature reactor system that's there now. The HTR is a 10 megawatt thermal power unit. In 2009, they carried out proof of concept development in their what's called the IS-10 system, which was sort of 10 liter per hour hydrogen production capacity unit. And later on in the 2014 period, they moved on to what's called IS-100 system that was capable of producing 100 liters per hour, shown here in this picture. It ran for something like 86 hours, producing hydrogen out of those 86 hours, 60 hours continuously at something like 60 liters per hour. They are also looking at materials currently and larger scale demonstration in the future. This slide shows their current and future activities in the area. One of the important contributions of Japan and China to the development of the sulfur-iodine process is the HI concentration technology, which is the EED, this electrodialysis system, where the HI is concentrated to overcome basically the azeotropic issues that they see. Again, they are looking at all the different sections of the whole process, simulations and coupling of the hydrogen production process to the HTR system. This slide shows actually this picture is their original concept demonstrations unit, and this sulfuric acid decomposer catalyst test results shown here are from the original studies. The various catalysts were tested, as you can see, and I think the copper chromate catalyst was the one that they settled on for their further work with the IS-100 system. These results are from the IS-100 system, where they ran continuously for 60 hours producing hydrogen at 60 liters per hour rate. So this slide is on the Korean activities. Korea earlier on focused very heavily on the sulfur-iodine process development. They were one of the main players. The current focus, however, is in sort of investigating the integration of the hydrogen production processes to VHTR systems, as shown here. They are looking at the high temperature steam electrolysis integration, sulfur-iodine process integration to the VHTR, and also steam methane reformers to the VHTR. The coupling of these SMR, the steam methane reformers, to VHTR does reduce the greenhouse gas emissions significantly through a reduction in the use of methane that's conventionally used to produce heat in the SMR process. Moving on to the high temperature steam electrolysis. As mentioned earlier, HTSE is the reverse of the solid oxide electrolysis electrolysis technology. However, the performance and the efficiency of the cells are quite different under these different operating conditions. The efficiency under the electrolysis mode is less compared to the under the fuel cell mode is less compared to the electrolysis mode. There are various reasons for the different behaviors under these conditions, as shown in this slide here. Originally, the original high temperature steam electrolysis had separate layers for the cell, electrolyte, the cathode layer, which is a nickel cermet electrode, the anode layer. These were all separate layers in the old technologies, where they were put together to produce a cell and then a stack. The latest technologies involve electrode supported cells, in which the anode and or the cathode electrode materials are coated onto the sides of the electrolyte. Here it's shown in white. Actually, all countries, US, France, EU, China, etc., have invested quite substantially in the development of the HTSE technology over the last little while. This slide shows the holistic approach that CEA in France has taken on the development of the HTSE, and they are extremely focused on the high temperature steam electrolysis. They've got, as I said, it's a holistic approach, and they look at the base materials, various components, development of the components, development and production of the components, preparation processes, system integration, and various demonstrations, including high performance, to show high performance, durability, and cost efficiency. This slide shows their sort of progress over the last 10 years that the hydrogen PMB has covered. Phenomenal cost reduction, as you can see here, 80% cost reduction through the various things that I just mentioned, and good lifetime achievements have been demonstrated. A prototype integrated system is also a great achievement over the last decade. The specific developments on module and systems is shown in this slide as a timeline. In 2014, the first 5 kilowatt electrical high temperature steam electrolysis system started. Then 2018, a reversible system. As I said, the electrolyzer can be operated as a fuel cell or an electrolyzer. So that was 2018, their first reversible system. It was delivered to ENGIE, and some details you can see here. And then 2020, again, multi-stack reversible system delivered to an Italian installation. And then current activities, which is supposed to progress until 2022, It's called Green Heat, which is a green industrial hydrogen 2 project to produce hydrogen for a steel mill to reduce steel. This slide basically just shows some interesting results on a 6 kilowatt electrical unit. Although the results are shown here for a short period of operation, interesting to see how you only just need to heat the electrical power requirement initially to get the temperature up, and then you basically shut down the heating part of it. And the internal resistant heating from the power supply to the unit keeps the temperature high, and you can produce hydrogen at a reasonably steady conditions without that electrical power for heating. So so this slide basically shows some estimation of the cost of hydrogen produced by high temperature steam electrolysis carried out by CEA. And it basically shows as a function of the scale of production, manufacture of these cells, and the cost of electricity, etc. The forecast is for something like 1 to 1.5 euros per kilogram. However, I should caution that some significant assumptions are made on lifetime of these cells, capital costs, etc. This slide shows the U.S. Activities, and U.S. has continued quite strongly in the development of and demonstration of the HTSE technology, high temperature steam electrolysis technology. This slide shows the nuclear hybrid energy concepts that they're looking at. What's called Detail Lab. It's the acronym for Dynamic Energy Transport and Integration Laboratory, and that includes the 25 kilowatt electrolyzer as part of this system. The effort the effort is focused on advancing the state-of-the-art state-of-the-art high-temperature electrolysis technology while demonstrating grid and thermal energy integration and dynamic performance characteristics. The effort is focused on these activities. The facility has been, this is the electrolyzer system, has been commissioned, and initial testing at the 5 kilowatt scale has been carried out. Actually, the US over a period of time was very heavily involved in the development of the high temperature steam electrolyzer components, and this slide shows that they worked with several manufacturers and suppliers of various components for the electrolyzer, and they tested them and worked with these suppliers. The suppliers are the manufacturers identified in this slide: Ceramatec, MSRI, Versa Power, Saint-Gobain, Rolls-Royce, etc. So there was a lot of work that went in the development of the various components at INL, Idaho National Lab. And this slide shows some of their initial work with, I think this is the MSRI unit, a 5-cell is a solid oxide electrolysis stack used as for for these tests. They demonstrated fairly good degradation, proper behaviors of the cell, and they ran it for something like 1,200 hours, as this figure shows. Actually, recent advancements around the world have demonstrated even a lot better lifetime performance of these cell designs. As I think I pointed out earlier, or not, I'm not sure, various countries in Europe are actively pursuing the high temperature steam electrolysis development. However, many of these developments are really linked to solar power rather than nuclear power. That is fine as long as the basic HTSE technology is developed for application with different energy sources. This slide shows the solar simulator providing the heat to the boiler here, the steam generator, and then the actual high pressure electrolyzer that they used to look at something. It's a small something like 7 liters per minute hydrogen production experiment. So moving on to the Canadian focus on the copper-chlorine cycle. So Canada has focused on the development of the moderate temperature. We call it moderate temperature because the temperature requirements are less severe. It's about 530 degrees C. As I pointed out before, there are 3 main steps involved here: electrolysis, hydrolysis, and decomposition. In the electrolysis, basically involves copper chloride HCl aqueous solution getting electrolyzed to produce hydrogen, and then CuCl2. CuCl gets oxidized to CuCl2, and there's a separation step here where this heat is provided, and then you basically produce CuCl2 for the next step, where it is hydrolyzed with reaction or exposure to steam at around 380 degrees C to produce an intermediate product called copper oxychloride, which is then passed to the decomposition step, where it's decomposed to produce oxygen and the CuCl required to complete the cycle. As I said, the maximum temperature is 530 degrees C for the decomposition step. Hence, you can use moderate temperature nuclear reactors, renewables, and even industrial waste heats. So the attractiveness of the CuCl cycle as compared to sulphur-iodine, etc., as you could have seen from what I've shown already, it's somewhat of a simpler process. The chemicals involved are not that bad, though the HCl at the concentrations that we use, there are significant limitations with materials, etc. But it's somewhat an easier process, and it does have high efficiency for better and better economics at large scales. As I said, low temperature. We can use the different reactor systems, ideally suited for coupling with heat sources. Small modular reactors is an area that that this copper-chlorine cycle can be coupled easily. As I said, materials of construction is not too bad, and the raw materials are inexpensive, and there's no requirement for catalyst in any of these steps, except the electrolyzer does have a catalyst on the electrode, but it is a well-established catalyst technology. However, there is a requirement for solid handling. That's the caveat here. That requires special considerations. This slide basically just shows a simplified integrated copper-chlorine cycle of the different steps that I talked about. This slide shows a MATLAB model that we sort of started with to look at the heat and mass balances. And now we've moved on to Aspen modeling for more detailed process engineering work, and also cost estimation, and also to look at optimization of the heat and mass heat balances. Heat balance is a heat requirement for this process is an important aspect that needs to be looked at very carefully, and we are using models to look at the best ways to optimize the heat requirements of the process. So this slide shows the electrolysis step, and this step was considered to be very difficult, a very difficult challenge in the past, but now it's well developed and well developed and well understood step. Lab system shown here is capable of producing hydrogen at 50 liters per hour or more. And long-term operation of the cell has already been demonstrated over a 1600-hour period. This slide 43, shows the separation of the various species, and it is not technically a challenging step, but it can be challenging from an energy point of view, energy requirement point of view. It is an energy intensive step. As I mentioned before, the current focus is on process simplification, minimization of energy requirements, and recovery of heat as much as possible. This step 40, the slide 44, is a hydrolysis step. It's basically you're hydrolyzing the CuCl2 with steam. It's been the most challenging step for continuous operation of the overall process, or to develop a continuous process. Progress is achieved, though a bit slow, but it is the current efforts are basically to make it more efficient and more amenable for integrating within the complete system. And there's also a collaborative development project underway with the Ontario Tech University in Ontario, Canada. This step shows this slide shows the decomposition step involved. This is basically the copper-oxychloride is decomposed to CuCl for recycling, and oxygen is produced here. This step is well developed at Chalk River at CNL. The unit shown in the picture can easily provide the required capacity for integration in the cycle to produce 50 liters per hour. Current focus is on optimization of the step for thermal efficiency and good gas-solid contact in the decomposer. So in Canada, CNL is sort of spearheading a plan to demonstrate this technology for industrial application. The current plan is by 2021 to put together this lab scale system to produce something like 50 liters per hour hydrogen using this process. Following that, the technology, the plans are to sort of pilot plant demonstration with commercial partners, and then further implementation for industrial applications. I didn't talk much about the hybrid sulfur cycle. The development of this technology has been sort of limited. In the early part of the first 10-year project arrangement of the hydrogen PMB, it was around 2008, there was considerable interest on this technology in the US. and there was some sort of good advancements were happening. Unfortunately, because of the down selecting that happened, this process also got skipped. But EU institutions have resumed development of this cycle for solar energy applications. Currently, INET in China is starting experimental work on the development of this electrolyzer, of the electrolyzer used for this process. So, in summary, I would say there's been very good progress demonstrated by the member countries, and these are captured by the Hydrogen Production Management Board. The operation of the integrated sulphur-iodine process has been demonstrated, so it's not really theoretical. However, there are materials-related issues that require a solution for industrial demonstration. High temperature steam electrolysis technology actually is a reasonably matured technology. However, this degradation of cell components requires continuing advances, and also still the costs related, the capital cost needs advancements, a reduction in capital costs, etc. The copper-chlorine cycle development is, as I mentioned before, is approaching lab scale demonstration. Operation of the integrated system. So it's the current some of the effort is in the solid transfer and also energy optimization. All the above hydrogen production processes still require demonstration of economical production capabilities. They've all been demonstrated reasonably well. But what I feel is that with advances through planned developments that are currently going on, there is very strong investments in these technologies. I believe it is believed that economical hydrogen production can be achieved with these processes. With that, I end my presentation, and thank you for listening to people all over the world. And I can take some questions, I think.
Thank you, Sam, very much for sharing your expertise with us. As questions are being typed into the question pane, we'll just take a quick look at the upcoming webinars. In May, performance assessments for fuels and materials for advanced nuclear reactors. A presentation in June on comparison of 16 reactors, neutronic performance in closed thorium, uranium, and uranium-plutonium cycles. And in July, a presentation on the overview of small modular reactor technology development. I'm getting a little bit of feedback from some of the participants that not all of the browser updates include the ability to see the questions pane, but I believe there's a chat pane that should be available. So if you don't see a question pane on your display, when you open up the control panel with the orange rectangle and the white arrow, the best strategy for getting your questions answered, I believe, will be sending an email, and we will just have to follow up in that regard. We do have several questions that have been typed in. So Sam, if you can see the questions pane, the first one deals with Gen 4 has 6 reactor concepts. Where does the SMR fit in? With SMR, what is the hydrogen production strategy?
So SMR sort of basically uses some of these technologies covered in the Gen 4 program. For example, Canada is looking at SMR technologies for for demonstration at Chalk River in Canada. And some of these technologies that we are looking at are really part of the Gen 4 systems. So as far as the hydrogen production is concerned, we would cover any work that's done with SMR that sort of uses some of these technologies, the either the gas cooled reactors technology, high temperature reactor technologies, um, or even low temperature sort of moderate temperature reactors like molten salt reactor systems. So these will be covered as far as I'm concerned with the hydrogen on the hydrogen side, on the hydrogen PMB.
Thank you. The next question reads, if money was unlimited, how fast could we switch to a synthetic liquid fuel economy for transportation? At the current rate of research funding and development, how long would it take to attain such a goal?
So actually the synthetic fuel, in fact, 39 years ago, I was at British Gas Corporation in the UK, and we were working on the syngas production. So the technology is there. I think is the willingness to make it happen is the issue here. So I think if there is a lot of money and there's the will to do it, I think it can be done now. I don't see it as a major problem. But remember that you have to remember is that the synthetic fuel processes also produce to some extent greenhouse gases, and that you need to sort of to look after how to get rid of the greenhouse gas or to minimize greenhouse gas emissions. So I think the technologies are there. They are not there. But it's just a matter of wanting to do it.
Thank you. What is the expected lifetime cycle of SEOC cells or stack in a medium term?
So in the medium term, I think 5 to 10 years is I think is what I've seen. And some of them are 3 years, but I think 5 to 10 years is reasonable.
Thank you. Ignoring hydrogen generation technical challenges, which reactor type is best suited to deliver the highest efficiency? HTGR?
So yes, because the high temperature gas cooled reactors can be integrated with the Sulphur-Iodine process or the high temperature steam electrolysis without any loss of efficiency due to sort of lower temperature operations. So if you can operate if your reactor can provide heat at high temperature at 800, 900 degrees C, then those processes, the hydrogen processes, will produce hydrogen very efficiently. So I would say yes, high temperature gas cooled reactors.
Thank you. There are two questions. Does it exist a special work package for safety within the current project?
Yeah, sorry, go ahead.
Do you want me to? Okay. The other one is pure water is a scarce resource. What is the price order of magnitude for the desalination and purification of seawater for compliance with HTSE requirements?
So the safety, yes, actually our work package 4 covers. I only said coupling, but I ignored, unfortunately. There's a lot of safety related aspects that are covered in the in the work package 4. So the various aspects related to the safety aspects related to coupling coupling the hydrogen production to the nuclear reactor, as well as individual the hydrogen production process safety issues themselves are looked at. Another item that's looked at is that in the very high temperature reactors, you do have tritium related issues. Tritium is generated in the core of the reactor, and aspects related to tritium, removal of it, or basically sort of containing it within whatever the heat exchanger or within the core of the reactor, etc. Those aspects are also part of the work package 4. So yes, safety is considered as part of the work package 4. So Berta, can you what was the second part of the question?
It talks about pure water being a scarce resource. What is the price and the order of magnitude for desalination and purification of seawater for compliance with the HTSE requirements?
It's a good question. I'm not sure whether I have a good answer for that. Yes, the water is important because you are splitting the water to produce hydrogen and oxygen. So in places where you don't have clean water desalination is a process. Desalination itself is not cheap. It's expensive, so that cost, I don't think anybody has. At least we haven't in Canada, but I don't think others have looked at this in detail to see how the impact of that on the cost of hydrogen produced by high temperature steam electrolysis or any other process.
Thank you. What will be the challenges on licensing the coupling NPP and hydrogen production?
So there will be challenges, but I don't think they're surmountable challenges. It is a chemical plant, so they're producing hydrogen, and there are, again, we as part of the hydrogen PMB, and also people with the various groups that are looking at hydrogen production using nuclear are sort of looking at the coupling aspects, the challenges, the licensing aspects of it. Personally, I don't think it will be a I mean, when it comes to nuclear reactors and doing anything with nuclear reactors, yes, there will be licensing challenges, but I don't think the problems are not that great. It's just basically it's a matter of going through that process and how you place the hydrogen production process in relation to the nuclear reactor system. Those are all will be part of the licensing discussions going forward. So personally, I don't think that it will be a major issue, and also all countries and all the nuclear reactor system people have come to the realization or appreciation that hydrogen production using nuclear is an incredibly clever idea, and people will find ways of doing it, licensing such hydrogen production using nuclear reactors.
Thank you. It seems that PMB now is looking at several different hydrogen production technologies. Do you think at some point the PMB would recommend to focus on just one very promising technology?
Actually, this was discussed 10, 15 years ago. Personally, I think all these different processes have merits under different reactor conditions, under countries that have various interests and things like that. So I would think the hydrogen PMB, there is no real issue in focusing on any particular project. In fact, there was a lot of focus on the sulphur-iodine process as part of the hydrogen PMB. So there isn't really an issue with having these 4 different processes as part of the hydrogen PMB, because there are different countries involved, and in the past there was South Africa involved, and now England is interested in joining. So these countries will have different interests. So I would think that we will continue. If anything, it might be a good idea to expand the hydrogen production process considerations as part of the hydrogen PMB. The idea is that when you bring different processes, different groups, different countries to look at these things, there can be some synergistic activities. And that can really lead to advancements in these processes. So I personally think the plan is not really to focus on one process, because we don't want to. We don't know which process at the end, or many processes in the end, will be successful for industrial implementation.
The next question reads, for example, Japan seems to be readying to transition to hydrogen-based vehicles. If, for example, 10 million vehicles were hydrogen powered with an average of 15,000 kilometers per year, how much hydrogen would be needed? That might be more math than we can do verbally.
Yeah.
I posted it for you to take a look at, though.
I'm reasonably good at math, but I'm not that.
There's another question similar that compares a price of gasoline to the cost of hydrogen equivalent.
Yeah, so actually right now, the cost of hydrogen is not that cheap. So it's I think it's something like $13-14 a kilogram for hydrogen if you want to gas to fill your hydrogen vehicle in places like California and California and all. But I think the issue here is that the cost of hydrogen is high right now because it's not produced. It's not produced in in a large scale, and large scale does bring the cost down quite a bit. And as I pointed out, as the French analysis shows, that you need to have large scale production of both the materials, components, and things to really to bring the cost of the hydrogen down. So when you do that, and I think it's happening. It's happening quite fast. The cost will come down, and when it comes down, then it'll be hydrogen cars. Well, the Japan can go to a hydrogen economy basically for their transportation side. I don't know whether that answered the question, but yes.
Thank you. What is the peak hydrogen production rate for the outline technologies in mass per unit time rather than volume per unit time?
Oh, so the plan, the thinking is that you want to be able to produce production at the rate that the SMRs, steam methane reformers, produce hydrogen at. So, I mean, 100 tons per day is not out of the realm to produce hydrogen in large scale. So, I mean, right now I think this, so 100 tons per day, or I think at the hydrogen plant that's being built in the U.S. right now. I've just forgotten the name of the company that produces it, that's building, and they're talking about 400 tons per day hydrogen. And these large-scale processes, like the copper-chlorine cycle, or the Sulphur-Iodine process, or even the high temperature steam electrolysis, you have to look at that kind of 100 tons per day kind of range.
Are there any ISO TC dedicated to topics discussed today, or is it purely an R&D maturity level?
No, there are ISO technical committees involved in the hydrogen production area in Canada and also in the US, I'm sure. So there's a lot of things going on right now. Safety aspects. Some of my colleagues are involved with some of the safety aspects of hydrogen applications, and also on the production side.
You kind of touched on this before, but there's a little bit of a follow-up. Early on with the VHTR and a hydrogen production plant, co-locating on proximity locating in terms of safety was a concern. Has any progress been made on this from a regulatory perspective? Is co-locating still the current thinking?
I think co-locating is still the thinking. So I should say that we haven't really done a whole lot of. I mean, a lot of the discussions as part of the PMB or general has been co-locating these hydrogen production processes, locating at a far away location. The hydrogen plant has its advantages as well as disadvantages. Then you have the transportation, the piping of the hydrogen to the site and things like that, or the heat to the hydrogen production process. There's a lot of losses and things involved. So I would think, right now the thinking is sort of co-locating it, and I don't think I've been involved with that much discussion on sort of separating it completely away, or putting the hydrogen plant completely away from the nuclear plant.
Thank you. What is your best estimate of deployment date for commercial-based?
So, if I'm partial here, but if the when we demonstrate the copper-chlorine cycle next year in a lab scale.
For commercial nuclear-based production of hydrogen.
Oh, commercial nuclear-based. So that, I think it's at least 10 years down the road.
Will nuclear-based hydrogen production be able to compete with REN coupled to low temperature electrolysis?
So, like what I said, if I understand the question right, the high temperature electrolysis has a distinct advantage in terms of efficiency. If you because it's at high temperature, it's operated at high temperature. There's very major efficiency improvements can be achieved. So it definitely can compete. I mean, it'll be a better process. It'll produce hydrogen. If the capital cost aspects are all sorted out, it will produce hydrogen at lower cost.
Thank you. What do you expect in the future regarding the cost of hydrogen when comparing electrochemical and thermochemical water splitting? I think that might be something you've touched a little bit on before too.
So it's electrochemical and thermochemical. So actually, some of the cost estimates for the thermochemical processes, including the Canadian Copper-Chlorine cycle, they are all in the same ballpark. They are high temperature steam electrolysis, as well as the thermochemical processes, hybrid. In our case, in Canada's case, is hybrid thermochemical processes. I think they're in the same ballpark. And one good thing about these thermochemical processes is that the scale can have a significant merit advantage for the cost of the hydrogen produced. So you can really produce very large scale hydrogen using the thermochemical processes.
What are the limitations and drawbacks of methane-based technologies? I think it's steam methane reforming, partial oxidation, et cetera, versus the copper-chlorine cycle technology.
So the main disadvantage of the steam methane reforming is that the amount of CO2 that it puts in. I mean, the whole idea right now is that we want to develop a process that is more so environmentally friendly. The steam methane reforming process, as I had mentioned in my presentation, sort of every ton of hydrogen produced puts something like 10 tons of CO2 into the atmosphere. So it's basically, it comes down to the environmental issues, really.
Can you share your opinion about which country may be taking the lead in hydrogen production with VHTR?
With VHTR. I would say China is very active. Hydrogen production, using one of the processes that I've discussed. They are quite aggressive in their development. They already have the HTR10 process as a HTR10 plan of a nuclear system. It's a small system, but they've got the larger one, the HTR. I've forgotten DM or something. Sorry, the HTR. It's gone. Anyway, so they have a largest system under construction, and China has their plan to couple the HTR10 to hydrogen production process. I think probably China will be the first one to do this, I would think.
Great, thanks. Just to follow up on one of the questions that you'd answered a couple questions ago, simple statement of REN is renewable energy. For industrial or even the JAEA demonstration, many sensors and a good INC process control system is needed. What work has been done in intelligent control systems?
It's again another good question. We from the involvement in the hydrogen PMB, we haven't really focused a lot on this aspect. I think it is needed because these are if you take the processes, they are complex processes. Well, perhaps the high temperature steam electrolysis is less complex, but the other processes are complex. So you would need to consider sort of this. And so far, we haven't really spent a lot of effort on this. It's been mainly the process development and getting the process to work, to look at the materials related issues and things like that. It's something to look at as part of the future program.
Thank you. Someone's pointed out that the handouts didn't download or open for them. So if you click on them, they should download and open. If they don't, I apologize. I'm not sure why that is. But I have posted a link that the PDF version of today's slide deck is posted and available at that link right now. So you can go there to get the slide deck. And then again, today's presentation is being recorded and we will upload the audio video portion as soon as it's done rendering, and just if you'll just give us a little bit of time to do that. Thank you for pointing that out. Light water reactor technology is a mature commercial technology. Would coupling LTE production plant to an LWR provide for a useful demonstration of nuclear hydrogen production concept?
Definitely, yes. In fact, any of the reactor systems right now available can be integrated with some of these technologies, that hydrogen production technologies. And so again, it's really the will to do this, and it will demonstrate the integration of the nuclear system to a hydrogen production process. So current reactor systems can be integrated with these processes. Of course, there will be a little a little bit of a loss in the overall efficiency of the production of hydrogen, but it can be done now.
What about environmental friendliness of coupling steam methane reforming and HTGR as an energy source?
Yeah, so I think I did point out there's clear assessment of this coupling steam methane reforming to a high temperature reactor. Korea has done quite a bit of work, and in fact, some of the other countries have also done this work. And we also in Canada, we have interest in doing it, and we've touched on it. So when you use the high temperature reactor, all what you're doing is that replacing some of the methane used to produce the heat in the steam methane reformer with nuclear heat. So it definitely reduces the CO2 emissions quite significantly. And there are numbers that unfortunately I can't remember the numbers right now, but there are clear numbers evaluated for this coupling.
Great, thank you. Thank you so much again, Sam, for sharing your expertise and taking the time to put your presentation together. Thank everyone else for attending. We had a great attendance today. Those are the list of questions that have been submitted. We've gone about 90 minutes. So if there's no further questions, I will bid everyone safe and farewell.
Yeah, thank you, Berta, for your help, and thanks to everybody who was listening. And I hope there's some extra support for hydrogen production using nuclear power.
Thank you again, Sam.
Thank you.
It was a great presentation.
Hi,
Yes.
Patricia. Thank you. And
Okay, goodbye, everybody.
okay,
Bye-bye.
bye-bye.